In this video, we are going to write the code for Vanilla GANs. So first of all, let's import what we need: TensorFlow, NumPy, and Matplotlib. Let's connect to the GPU. As discussed, the noise shape is going to be 32, and it's time to create the generator in the GAN architecture. So the generator code is going to look something like this. Since we are creating vanilla GANs, that's why we are just using dense layers, no convolutional, nothing else. And we have discussed this code in the previous video. So let's run this cell. Let's create here the discriminator class, and it also has just dense layers, no convolutional, and pass the input from the flatten first in order to flat all the activations, because here, as you can see in the generator, the last layer is reshaped. So the output from the generator will be batch size into 28 into 28. So we need to flatten that 28 by 28 dimension. That's why we are using here flatten layer first, and then pass the output of the flatten to these dense layers. Let's run. And let's combine these two classes into a single class. I'll call this class GAN, and in this class I'm not going to create the object of discriminator or generator just like we did with variational autoencoder or standard autoencoder, because as you remember, in each training cycle we are going to make the discriminator either trainable or not trainable. That's why we are going to pass the objects of generator and discriminator to the GAN from outside, so that we could deal with it easily. Otherwise, if you have created the objects right here, then you have that dot convention. You need to write GAN dot discriminator dot trainable is equals to false, so that makes things a bit complex. That's why I'll keep it as much simple as I can, and I'm going to pass the objects. Then we are going to assign this self.generator, the instance variable, to the generator, and this self.discriminator to the discriminator object. And in the call method, I'm going to first pass my inputs from the generator and then the output of the generator as an input to the discriminator, and finally I'll return the output of discriminator from this GAN object. Now let's create objects of these classes. So here, as you can see, I have first created the object of generator, and I have passed my noise shape because it is accepting the noise shape right here, and that noise shape is going to determine the input shape for our first dense layer. Obviously this step is optional, because when you will run your model for the first time, the TensorFlow framework is automatically determine the inputs for each of these layers. Let's run. So after creating the objects of discriminator and generator, I'm going to pass them as an argument to this GAN class so that I could initialize them right here. Now the loss function for our discriminator is going to be binary cross entropy, because it is going to output either true or false, 0 or 1. So that's why binary cross entropy. And the loss function for our GAN is going to be binary cross entropy, because in this GAN architecture, what is going to be the final output? It will be output of this discriminator. So the GAN is going to output 0 or 1 as well. That's why the loss function for the GAN is going to be binary cross entropy. So here, as you can see, discriminator.compile, I'm going to provide my loss function, and then the optimizer is going to be RMS prop. You can test it with Adam and see if you can improve the model performance, but I'll stick with RMS prop. And then this step is really important. Okay, so it is really important, and sequence should be like this. Before compiling the GAN, we are going to set the trainable parameter to false, otherwise it is not going to work. You can't say first compile the GAN and then say trainable parameter to false. We will manually turn it on and will manually turn it off. So during the compilation process, we have to keep it off in order to make things work fine. So just make the trainable parameter to false of the discriminator and then compile the GAN. Now I'm going to create another helper function which will help me visualize the predicted images during the model training. So this is going to be my function, and it says show images and it takes images and the file name. It is also saving actually those predicted images, and by the end of training we will create a GIF of those images and it will really look awesome. As the name suggests, it is the number of columns in our plot. And it's time to create our training step. So this is the code. First of all, this function is going to take GAN as an input, the dataset on which we want to train this GAN, then the noise shape, because based on this noise shape, we are going to sample our noise from the normal data distribution, and then the number of epochs. From this GAN, I'm going to extract its generator layer and discriminator layer by typing GAN.layer. So it is going to return me the generator and discriminator. And then I'm going to write my for loop. So this is like the main for loop for number of epochs. I need another for loop that will iterate on batches. So these real images represents my batch. Then I'm going to say real images dot shape and will pass 0 argument, and this will return me the batch size. As you remember, firstly in the list we have the batch size, then the height, then width, and then number of channels. So with this index 0, I'm going to access my batch size, and this is going to work in our case because we are going to run it in eager mode, and in eager mode this dot shape works. If you are running it in a graph mode, then dot shape isn't going to work. Then you have to use this tf dot shape and it will return you the shape. Just pass here the real images, and then you need to say the square brackets and 0. So with graph mode, this is how you are going to access your batch size. But since we are running it in eager mode, that's why we don't need to use that dot shape and extra syntax. Once I have the batch size and the noise shape, all I need to do is to sample noise from the normal distribution. Then we are going to provide that noise to the generator, and generator will convert that random noise into something meaningful image, and I'll call that meaningful image a fake image. And here I'm going to create my dataset. I'm going to mix my fake images with real images, and this tf.concatenate will basically concatenate my images based on the batch dimension. So axis is 0, this means it is going to be the batch dimension. For example, if these fake images are 32 by 28 by 28 and real images are 32 by 28 by 28, then the output from this concatenate will be 64 by 28 by 28. Similarly, I'm going to create labels, and now I'm going to set my discriminator.trainable to true. So here I have accessed my discriminator and generator of this GAN, and I'm going to manually put this discriminator.trainable to true, and then I'm going to train the discriminator. So if you have watched some other YouTube videos or any other course on GANs, you might have observed that most of the instructors are using here that tf.gradient tab method and manually applying optimizer and calculating gradient. So obviously if you are feeling comfortable with that method, you can try it, but I think for beginners that will be overwhelming. That's why I'm going to stick with this train on batch method, which is quite easy, and it hides all the underlying complexity of training. Once I train my discriminator, then in phase 2 I'm going to generate fake labels for my fake images. So images are fake and the labels for them are fake as well. Then I'm going to put this discriminator.trainable to false. It's really important. Here we have enabled it, and now we are again disabling it because you are now training the generator only. And then I'm going to say GAN.train on batch and will pass my noise and the generator label. So in GANs, this noise will be first passed from the generator, and generator is going to convert that random noise into a fake image, and then we are going to pass that fake image to the discriminator, and discriminator is going to output either 0 and 1, and we are going to then compare that 0 and 1 with this generator labels. And this is how we are going to train our generator. Now let's run it. If you remember, we haven't prepared our dataset yet, so let's prepare the dataset. I'm going to use MNIST digit dataset, and again just convert it to float 32 and then divide it with 255 in order to normalize it. And now the batch size is going to be 32, and I'm going to convert these arrays to my tensor dataset object, and then I'm going to batch them and prefetch them. So prefetch is going to avoid that CPU GPU bottleneck. It will keep a batch ready in the memory to be fed to the GPU, so our GPU isn't going to face that data starving problem. And now let's train it. So I'm going to keep number of epochs to 20 for the sake of this video, but obviously you can keep it to 50 or 100 for better output. Once training is done, if you open your folder, you will find all the generated images during each epoch. So for example, if I open this one, and this is how our first epoch prediction looks like. Now, using these 20 images, what I am going to do is to create a GIF. So let's write the code. It's very simple. We are going to use the image IO, and this is the function which will help us create the GIF. So if you want to remove the generated images, then keep this code. Otherwise, let's remove it because I want to keep a copy. And then this is going to be the format. Let's run it. And yes, GIF is created and it is right here. Let's open it. Yeah, it seems pretty good. Since I have kept this FPS to 1, so this is 1 frame per second, that's why you might find it a bit slow, but you can obviously change it from like 1 to 2 or 3, 4, how many frames you want in a second. And in the next video we are going to talk about another variant of GAN, and I'll see you there. Bye bye.